Hello everybody, and today I would like to finish the proof of necessary condition for the local extremum. So let me recall what we are doing. What we know that the point x0 in Rn is a critical point, so it means differential of our function f at x0 is identically 0, and also we know that second differential is an indefinite quadratic form. So we want to prove that there is no extremum at x0, and we proceed similarly to the proof of part 1, and part 2 is analogous. So we consider Taylor formula, which says that f of x minus f of x0 equals to 1/2 differential plus little o of the norm of the vector x minus x0 squared as x tends to x0, and differentials here are just coordinates. So I from 1 up to n. So here we consider x as a point with coordinate x1, so on xn, and x0 is a point with coordinate x01, so on x0 more. Once again, maybe I mixed. I think xi not, or do you remember? I not, like that. Okay. So it's better, yeah. 1 not, so on x n not, yeah, like that. So that is the main base for the proof of the first part, and now we'll use it also. So what means second differential is an indefinite quadratic form. So if we write second differential, we can write it, for example, in such a form. So sum I from 1 up to n, sum j from 1 up to n, second differential f, second derivative, sorry, dxi dxj and x0 times, so here xi minus xi naught, xj minus xj naught. Okay. So we have a quadratic form. So quadratic form, let's say quadratic form of variables xi1, so on xin, let them to be, then we have, this is our quadratic form. Our quadratic form, psi I, psi j. Then, so we know this quadratic form is indefinite. So Q is indefinite. Q is indefinite. What it implies? It implies that there are two vectors. Let's say I use only coordinates psi1, 1, so on, psi n 1, and psi 1, 2, so on, psi n 2. There are at least two variables xi's such that Q of psi 1, 1, so on, psi n 1 is positive, and Q of psi 1, 2, so on, psi n 2 is negative. So indefinite quadratic form means that we can find two sets of variables such that our quadratic form has opposite signs. Then what we'll observe? So if we'll substitute now, let's say Q of rho times psi 1, 1, so on, rho psi n 1, then what it is? Maybe I'll put here I, and then we put I either 1 or 2. That is, if we substitute everywhere rho times psi instead of psi. We have rho squared as a common multiplier, so that is rho squared times Q of psi 1 I, so on, psi n I. And it means that our Q preserves the same sign as here, right? So the sign of this value is the same as the sign of Q. What it gives to us? Now, we observe that norm of the vector rho psi 1I, so on, rho psi n I is equal to rho squared times norm of vector psi 1 I, so on, psi n I, and this tends to 0 as rho tends to 0 plus, right? Doesn't matter which vector, what is the norm of the original vector, psi 1 I and so on, psi n I. Hence, we can substitute just dxi, let's say j, let them be to equal rho times psi. Okay, maybe I'll change here I, there j, psi j I, j from 1 up to n, and I 1, 2. So these are values of differentials. So instead of xi minus xi naught, we'll substitute that one. So in other words, xj equals to xji equals to xj0 plus rho times psi ji, j from 1 up to n, I from just 1 and 2. So these are points x. These are points x. Then what happens? So rho tends to 0, hence points x I tends to x naught. I 1, 2. Because of the construction of those values, right? And now, if I'll substitute that xi minus f of x naught, if I'll substitute into our differential, so that is 1/2. Let me recall, second differential is just quadratic form q for those values. So q for rho xi 1 I, so on, rho xi and I, plus little o, okay, this is not a vector, just that one, little o of rho squared, because if x tends to x naught, then rho tends to 0 and vice versa. That is valid as the rho tends to 0. So it follows from our Taylor formula when we'll substitute those particular values of xi's. These are vectors. And I here 1 and 2, just two values. Okay, then that is, you see, rho squared times q, and it means that if I equals to 1, then the right hand side has the form 1/2 rho squared times q of xi 1 1, so on, xi n 1 plus little o of 1. I'll take rho squared as a common multiplier. And then you see what happens. This quantity tends to, as rho tends to 0, tends to q of xi 1 1, so on, xi n 1, which is positive. Hence, the whole term in brackets is greater than c, which is positive number, a positive number, for sufficiently small rho. So we know property of the limit. So if we have some quantity which tends to a positive number, then for sufficiently small values of rho, this quantity is also positive, separated from 0. So greater than c, a positive constant for sufficiently small rho, right? And then what we have? So the right hand side has the form rho squared times something positive, separated from 0, right? And it means that the left-hand side for I equals to 1 is positive for sufficiently small rho. Right? So you see that rho tends to 0. The point xi tends to x naught. So we know that as close to s naught as we want, we can find points where this difference is positive, right? And analogously, if we consider I equals to 2, we choose other sequence, not a sequence, that is in fact a family of points. In fact, that is a line. We go along a ray or line, rho tends to 0. Yeah, if rho is positive, then this is a ray, but we can consider arbitrary sign, it's not important. So if I equals to 2, then f of x2 minus f of x naught will be analogously negative for sufficiently small rho. And it means that, you see, in arbitrary neighborhood of x naught, we can find points where this difference is positive and where this difference is negative. Hence, the point x naught cannot be a point of extremum. And the theorem is proved finally. And let me recall Sylvester criteria. Did you study it? Yeah. So quadratic form, the quadratic form Q of, let's say, psi1 so on psi n is positive definite if all principal minors of the matrix of the form are positive. Right? That is the Sylvester criterion for positive definiteness of the form. What's about negative definiteness? Signs should alternate, right? What you can deduce easily by considering the form minus q. Okay, so corollary of our theorem, corollary. If x naught, y naught is a critical point of twice continuously differentiable function f of xy, then first, if second derivative dx twice at x naught is positive and the product of those x naught, y naught times y naught minus second derivative dx dy x naught y naught squared is positive. And let me denote it by h x naught y naught. Then x naught y naught is a point of strict, in fact, strict local minimum of f of x, y. If second derivative with respect to x at x naught y naught is negative and h x naught y naught is positive, then x naught y naught is a point of strict local maximum of f of x, y. And third, if h of x naught y naught is negative, then x naught y naught is not an extremum point of f of x, y. The third part of this corollary follows from another part of Sylvester criteria. I didn't cite it here, but I guess you remember, right? So if quadratic form, if not, that is true just for two variables, right? Yeah. Okay. And let me mention also one. I forget also to say this H is called Hessian. That is the determinant of the matrix of second of this. So that is the matrix and the matrix of the form, and here I wrote the determinant of that matrix, and that is called Hessian. And also for several variables, you can consider analogous determinant, but then you will need to consider all principal minors also, right? Yeah, and you see, there is a question what to do if, let's say, our Hessian is 0. Because in that case, no assertion in the corollary, right? So what to do? In fact, there was an example. I mean, x power 4 minus y power 4, right? And it was an example where Hessian is 0 at the origin and no extremum at that point. In fact, it was saddle point, but there are even more complicated examples of the behavior of the function near a critical point with 0 Hessian. And I mentioned to you a wrong definition of surface area. During second semester, I mentioned there was a wrong definition of the area of the surface, which was similar to the definition of the length. I mean, the length is supremum of lengths of inscribed polygonal lines, right? That was the length. So the length of the curve is supremum of the lengths of polygonal lines inscribed to the curve, right? And there was a wrong definition of area surface, which said that area of a surface equals to supremum of areas of polygonal surfaces inscribed into your surface. And it was wrong because of an example I gave to you, that example Schwarz lantern, right? And surprisingly, that the same author of this wrong definition also, he wrote in his textbook on analysis another wrong assertion which was related to extremums, extrema. He said that so if second differential at the point is 0 and third differential is 0, but fourth differential is, let's say, positive or negative, where second and third are zeros, then the function has a local extremum. And it was also wrong. It was also wrong. So, and there is a simple example which is called Peano surface. Peano surface. It's 2y squared minus 2x squared minus y times y minus x squared. That is Peano surface. Peano surface, the graph of that function. And sometimes also it is called Peano saddle. What is interesting here? You see, this surface has the following property. If you fix x, so you consider one vertical plane, then if you fix x, you have local maximum at the origin. If you fix y, you have local minimum, right? That function has a quite different nature. Here, doesn't matter which function, so let's say x equals to 0, you have minus y squared, so you have maximum, right? If you fix y equals to 0, you have minus 2x power 4, also maximum, right? But also, if you consider arbitrary vertical plane through the origin, right? You have a function of one variable, which still has a local maximum at the origin. But the function has no local extremum at the origin. because if you fix, let's say, y equals to 3 over 2 x squared, right? Then you see that is yeah, positive, and here also positive, right? So along y equals to 3x squared, the function has local minimum at the origin. So it means there is no local extremum at the origin. You can find nice pictures of this surface in Wikipedia, let's say. Just click Peano surface and nice pictures of this Peano saddle. Okay, so now next topic which we'll discuss, it's a little bit similar to what we did, but now there is relative extrema with constraints. So definition. Let f be defined on an open set G in Rn. X naught belongs to G. G intersected with E, where E is the set of x's in Rn such that phi j's of x are zeros, j from 1 up to m less than n. Phi j's of x are zeros, j from 1 up to m, that is 1, are called equations no, just constraints. That is equations called constraints given by equation. I'm quite sure that later you will consider linear programming, I mean simplex method and other optimization methods where constraints given by inequalities will be considered as well. But here we'll discuss only constraints given by equations, nothing else. I need number later. Okay. The point x naught is called a point of relative maximum or minimum of f with constraints 1 if for all x in a neighborhood delta, or maybe if there exists delta positive such that for all x in the neighborhood intersected with E, we have f of x less or equal f of x naught for maximum, and for minimum the inequality is opposite. Of course, if you have strict inequality for x not equals to x naught, then this is strict relative maximum. I will not give precise definition. So, you see, the most important thing is that one. Relative maximum minimum with constraints means that we ask for this inequality not for all values of x, but only when x satisfy equations 1. And as another rule, the number of equations should be less than n. Otherwise, too many restrictions. Okay, so how to try to solve such a problem, to find a relative minimum or maximum? Let me firstly to analyze the problem generally. So, when you have such a problem, such a kind of problem, there is one possibility, namely, look at the system of inequalities. You have a system of equations, right? You have m equations with n variables, so overdetermined system of equations, right? So maybe you are able to solve that system of equations with respect to some variables, right? If you will solve that system of equations, then you may express part of variables in terms of other variables, right? And then you substitute those expressions into your function, and you get a function of smaller number of variables. But now you can consider the problem of extremum without constraints. So what was solved before? And that is, sometimes it's possible. But of course, in general, it is more complicated to solve the system of equations. I mean, if it is nonlinear, for example, of course you can solve a linear system, but for nonlinear, that is different story. So in most cases, you cannot solve the system of equations 1 explicitly, and then you can apply other methods. Oh, we have a break. Very good. Let's continue. And so let me describe now in more details this, let's say, first way to solve extreme problems with constraints. So, suppose rank of the Jacobian matrix, so d phi 1 with respect to x1, so on d phi 1 with respect to xn, so on d phi m with respect to x1, phi m with respect to xn, at x0. So it means that all partial derivatives are taken at x0. Rank is maximal, equals to m. Because you see, here the Jacobian matrix is m times n matrix, right? So maximal rank is precisely m because m is less than n. Then there is a minor of order m with non-zero, right? There is a non-zero minor of order m, right? Let it be the principal, so phi 1, so on phi m with respect x1, so on xm. Just the principal minor, so the left part of our matrix has non-zero determinant. Then, by theorem 2 of former section, that is implicit functions given by a system, right? By a system. Theorem 2 of former section. Which section it was? 5, right? This section is section 6. This 5. So former is 4. Section 4. Section 4, right? Given by a system. So if we have determinant Jacobian with respect to a part of variable of this system is not zero, then we can solve it. So there are functions let's say x j are equal to psi j of x m plus 1 so on xn, j from 1 up to m, such that the system 1 is equivalent to xj equals to psi j xn plus 1 so on xn, j from 1 up to n, to this system, right? And let it be 1 prime. So that is 1 prime, right? That is 1 prime. And this equivalence in a neighborhood, let's say neighborhood of x naught. So I'll not use once again epsilons, cube, and so on, right? Just a neighborhood, let's say, short. So you see, this system is equivalent to system 1 prime. I prefer to numerate equations with primes because of, you see, later it will be better to compare things which are obtained when we use the original variables and we use only part of those variables and avoid other. Okay. So the problem to find the relative extremum of f at x naught under with constraints. One is equivalent to the local extremum problem for the function capital F, which depends only on the variables xn plus 1 so on xn. How? What we should do? We substitute into our function f. Instead of x1 we substitute psi 1, so on, psi m, and then the rest of variables as they were. Yeah. For the function at x naught tilde, which is x n plus 1 tilde, so on, x n tilde. Oh, so not tilde, x n plus 1, 0, so on, x n 0. Why that is true? Because look, so we were interested in the extremum of this function f of x1 so on xn when variables x1 so on xn satisfy constraints 1, right? Now, constraints 1 are equivalent to expressions of part of variables, right? Here is j. Part of variables in terms of the rest of variables. So if we'll express those variables, you see, x1 so on up to xm, we express in terms of others, right? If we express, it means it's equivalent to consider only points which satisfy 1, right? So when x belongs to this intersection, it's equivalent that we consider only points with those coordinates, right? In the neighborhood of that coordinate, right? But instead of f, we consider capital F, where all other variables are expressed through our part of variables, right? That is how we can solve that problem. Yeah, that is the first way. Unfortunately, in very rare cases, we can do it. That is rather seldom, right? When we can solve a system of equations. Generally, it might be nonlinear, right? Then we use another way. So for second way is to use the Lagrange function. So what is it? Definition. So the Lagrange function for the problem of relative extremum of f with constraints 1 is L of x1 so on xn lambda 1 so on lambda m equals to little f of x1 so on xn plus lambda 1 phi 1 x1 so on xn plus so on plus lambda m phi m x1 so on xn, and lambda 1 so on lambda m are called the Lagrange multipliers. So instead of considering our original problem for relative extremum, we form new function which includes everything, you see. The original function which we want to study, right? Plus all constraints multiplied by some multipliers. And it turns out that after that we can reduce our problem to solve the relative extremum to the problem to solve the usual local extremum, but for the Lagrange function. That is the crucial thing. So you see, you don't need to solve any system of equations. Just write the sum and write extra variables. And surprisingly, it's enough to solve the problem. That is very wonderful thing. And of course, we need to prove that indeed this works, right? And how it works. And you see, what is the main problem? You see, the definition was given if a point is a point of relative extreme, right? So you consider a point, you have the definition of relative maximum or minimum, right? But the question, how to find such a point, right? That is the main question. So you don't know that point. That is the question. And so you need to find the point where maybe you have this relative extremum. Okay, then, so now I'm ready to formulate theorem 3. Necessary condition for relative extrema with constraints. If x naught in E, let's say, right, is a point of relative extrema of differentiable function, f with constraints 1 and the rank of the Jacobian matrix okay, let me rewrite it. D phi 1, dx1, so on, d phi 1, dxn, d phi m, dx1, phi m, dxn is maximal at x naught equals to m, right? Then there exists a unique vector of the Lagrange multipliers lambda naught, lambda 1 naught, so on, lambda m naught, such that x naught lambda naught is a critical point of the Lagrange function. L x1 so on x and okay, maybe x vector lambda vector shorten. Yeah, so you see, if some conditions, not so many in fact, you see only rank of the Jacobian matrix should be maximal. Yeah, of course, yj should be continuously differentiable, that is with, or maybe with continuously differentiable phi j's in the constraint. Yeah, that is important. With continuously differentiable phi j's in the constraints 1. So all functions phi j in 1 should be continuously differentiable. That's also important. Okay, so you see what the theorem says. Like for local extremum, I don't know, maybe you solved also in seminars even for several variables. I don't know if you solved or not. Not yet? You? In the same group. I see. Not yet, right? Second, I think it's from third. Yeah, I see. I see. Yeah. So, but you see, you solved problems for local extremum for functions of one variable, right? For one variable, what was the first step? You try to find critical points where derivative is 0, right? After that, you check if there is an extremum, right? So the first problem is to find suspicious points, right? Critical points. They are suspicious for extremum. And if you want to solve relative extrema, it means you want to find extremum of a function f on the constraints, right? Then what you should do? You form the Lagrange function and then solve the problem of local extremum for this Lagrange function, firstly, just to find suspicious points. Differential should be 0, right? That is the necessary condition for extremum of the Lagrange function. So with necessary condition, it's relatively easy. For sufficient condition, it will be a little bit more complicated. Okay, now proof. Yeah, I think. Yeah, I think I'll be able to prove it. Yeah. Okay. So, proof. Without loss of generality, suppose that the principal Jacobian is not 0, and x0 is not 0. Then, like it was mentioned before, then 1 is equivalent to xj are equal to psi j of x m plus 1 so on xn, j from 1 up to m, that is 1 prime, in the neighborhood of x0, right? So, and the problem not the problem, and no, and f, little f, has a relative extremum, and little f has the relative extremum with constraints 1, if and only if capital F of xm plus 1 so on xn, which is I didn't put, maybe I'll put the number. I think did I write the number? I think 2. No, not yet. No number. So let me write without number. F psi 1 xm plus 1 so on xn psi m xm plus 1 so on xn xm plus 1 so on xn. Yeah, that is capital F has the local extremum at x naught tilde, which is xm plus 1 0 so on xn 0. By the necessary condition, by it was theorem 1, sorry, right? By theorem 1, necessary condition right? So if x naught is a point of local extremum, so x naught tilde is the local extremum point, implies the differential of f, capital F, at x naught tilde is identically 0. That is necessary condition, right? Necessary condition. So if we are looking at the local extremum, then that is the condition. Now we have first differential of a function of several variables, right? But look, the function capital F is nothing else but the function little f, where we suppose that the first variables x1 up to xm are not independent, but they are functions of the others, right? But remember very important property of the first differential. The first differential is invariant. It means the formula for the first differential is valid in both cases. Either variables are independent or they are functions of some independent variables, right? It means that the differential is 0. It's equivalent that df is 0 at x naught, right? Or better to say, I want to use only that one. So implies that this differential is 0, right? Implies that this differential is 0. Where I just, yeah. So what is it? This differential is 0. It means, yeah, let me write it explicitly. Sum I from 1 up to n, partial derivative of f with respect to xi at x0 times dxi is 0, right? That should be 0. But remember that here differentials of xi, here they have a different nature. Namely, here dxm plus 1, so on, up to dxn, are independent, right? And dx1, so on, dxm, what they are differentials of psi1 xm plus 1, so on xn, so on psi m. Right? So we wrote this. Yeah, and yeah, now I should put number 2, yeah, number 2. That is number 2, that is number 2, number 2. Okay. Okay. Now I think I can erase. Time. I should think where to stop. Okay. I think I'll enumerate main ingredients and then I'll start next lecture with the list of main equalities. So what means their differentials? I.e. their differentials, I'll write the corresponding equalities. dxj equals to the sum I from m plus 1 up to n, partial derivative of psi I with respect, psi j with respect to x I at x not tilde vector times dxi, that is valid for j from 1 up to m. And this will be 3 prime. So I started with 3 prime, and then why I wrote 3 prime? Because I said that I prefer to use prime when we express part of variables, right? Here I express part of variables. But remember that functions psi's were obtained as a solution of the system 1, right? So when we differentiate, it means that to differentiate functions psi is equivalent to differentiate 1, right? So to differentiate functions 1 prime is equivalent to differentiate the system 1. And now I want to write down what means to differentiate the system. So if we differentiate the system 1, what it gives to us? Sum I from 1 up to n. So I differentiate every function. Derivative phi j with respect to xi at x naught times dxi. All of them are zeros. J from 1 up to m. And that is 3. So you see, the system of equalities for differentials 3 prime was obtained by differentiating 1 prime. 1 prime I erased, unfortunately. That is xj equals to psi j of xm plus 1, so on xn. That is 1 prime, right? So if we differentiate 1 prime, we obtain 3 prime, right? 1 prime is equivalent to 1. If we differentiate 1, we obtain 3. So 3 is equivalent to 3 prime, but in terms of differentials. Okay, and I think, yeah, now makes I'm not able to proceed further. Yeah, I'm not able to proceed further. No, I think I should stop now. Makes no sense to continue. Okay, that's all for today.